let's have a little bit of a further look at our idea of motion and using derivatives. I've got a velocity time graph here. So we're basically looking at integrating. Now when we talk about a picture, integration could also be thought of as area. So I don't actually need to integrate this function. Notice I don't even know what this curve is. But if I was able to find the area or estimate the area, I could estimate the change in displacement, because the change in displacement would be equivalent to the integral from 0 to 4. Notice it's the integral though, not the area. If I wanted to know the change in distance, then it would be the area. Okay? So remember how the area is different to just the straight integral. So the straight integral is like displacement, whereas the area under the curve would be like the change in distance. Okay. And we could do a similar thing if we had an acceleration time graph. If we wanted to find the change in velocity, that would be the complete integral, whereas the change in speed would be the areas under the curve added together. So this brings us on to, okay, derivative graphs. So some ideas here. Displacement, if we think of displacement as the function, then I know the first derivative is velocity, and we know the second derivative is acceleration. So on the original graph, on the displacement time graph, where I have a stationary point, if I was to draw a velocity graph, I must have an x-intercept, because stationary points occur when the first derivative is 0. If I had an inflection point on the original graph, then it would be a stationary point on the first derivative graph. And it would be an x-intercept on the second derivative graph. Now, how do I know that? It's probably more that I know it's going to be an x-intercept on the second derivative graph. Because remember, points of inflection occur when the second derivative is equal to 0. So I know that the second derivative is going to be an x-intercept. So logically working backwards, if I know that when I have a stationary point, then on the next derivative's graph it's an x-intercept, it makes sense that the first derivative would be a stationary point. If the original graph is increasing, then I know the first derivative graph will be above the x-axis, or t-axis if we're talking about time. And if it was decreasing, I know it'll be below. If the original curve is concave up, then I know that the velocity graph will be increasing, because the second derivative must be positive. If it's concave up, the second derivative is positive. So logically, again, working backwards, well, if the second derivative was positive, it must have come from an increasing graph. So the first derivative would be increasing. And so concave down, the first derivative would be decreasing because the second derivative is negative. And so that's a way we can create, well, not only displacement, velocity, and acceleration, any kind of derivative graphs. If they give me a graph of a function, I could create the derivative graph, or if they give me the derivative graph, I could work backwards and create the original function by looking at key points. So graph types then, if the original graph was a horizontal line, when I integrate a horizontal line, I'm expecting an oblique line, because a horizontal line would be y equals a constant. Integrate a constant, you get some multiple times x. So an oblique line. If I was to differentiate it, then it'd have to be the x-axis, because differentiate a constant, you get 0. If the original graph was an oblique line, then when I integrate it, I should get some sort of parabola. Might not be the whole parabola, it might just be a piece of it. But it should be that sort of curve, because when I integrate something times x, I know it'll go to x squared. So I must end up with a quadratic. If I was to differentiate it, then I would get a horizontal line. And if it was a parabola, then when I integrate it, I would get a cubic graph. And and it would inflect at the turning point of the parabola, the same x value. And it would be an oblique line if I differentiate it. So things to keep in mind, integration gives us areas. That's what we use integration for. So on a velocity graph, the total area is distance, whereas the total integral is displacement. On the acceleration graph, total area is speed, whereas the total integral is velocity. So let's have a look at some HSC questions where they've given graphs and sort of asked you to get information using this sort of idea. So velocity 2 minus 4 cos t. V is measured in the usual things, meters per second. So at what times is the particle at rest? Well, we know that's when velocity equals 0, so we can solve it, and we get, it's in the first and the fourth quadrant. We're going to have, there they are, pi on 3 and 5 pi on 3 for our little domain of 0 to 2 pi. Maximum velocity, oh, see, they did use that term. Gee, I hate that. Maximum velocity. I maintain they should say maximum speed. But anyway, fortunately, the answer is the same. Because if minus, I think it's the same, because if minus 4 cos t, we know goes between minus 4 and 4. So 2 minus 4 cos t must go between minus 2 and 6. So therefore, the maximum velocity is 6, which does also turn out to be the maximum speed. So in this case, I guess they could get away with using the term maximum velocity rather than maximum speed. Sketch the graph. Okay, we know the amplitude is 4 units. Shifted up 2, it's flipped upside down because of the negative. Period's 2 pi, so I'll do my divisions every pi on 2. So here we go. We got a cos graph. Cos graph would normally start at the top of the amplitude, but this one has been flipped upside down, so we're at the bottom, but we've also been shifted up. There's my axis. So I'll start down here at negative 2, then we'll go up and down, and there's my graph. Okay, so we've sketched our graph. Calculate the total distance travelled by the particle between 0 and pi. So it's distance, so I've got to break it up into its areas. So it'll be the integral from minus, because that's below the axis, from 0 to pi and 3, plus the area from pi and 3 to pi. The other thing you can do with trig graphs is remember they're symmetrical as well. So you could work out like quarters and then say, well, that area is going to be the same and so on. But anyway, let's do our integration. 2t minus 4 sine t, subbing in, oh, what a lovely distance. 4 root 3 plus 2 pi on 3 meters. But you probably guessed that anyway. I mean, well. 2004 one. Here's a graph where it's an acceleration time graph. They haven't actually given us an equation for the different bits, but I suppose because they're straight lines, they'll be easy enough to work out. So initially it's at rest at the origin, and we're going from 0 to 5. Okay, what do they want us to do? Write down the time at which the velocity is a maximum. So all we have is an acceleration time graph. We want to know when velocity is a maximum. So when velocity is a maximum. Now we know velocity is the integral of acceleration, or another way of thinking about it is acceleration is the derivative of velocity. So the acceleration, or that area, or integral, will be a maximum at t equals 2. Or another way of thinking about it is, if I'm saying velocity is a maximum, its derivative, which is acceleration, must be 0, because that would be the stationary point. And if we look at our graph there, the acceleration is 0 at t equals 2. So that's another way I could think about that. So either way, velocity is going to be a maximum at 2 seconds when we read off that particular graph. It then said, at which time, or what time, is the particle furthest from the origin? Furthest from the origin. Okay. So it's saying, when is displacement a maximum? When's the displacement a maximum? So displacement will be a maximum when velocity is equal to 0. But velocity is the integral of acceleration. So for it to be equal to 0, if I'm looking at my graph, I want to solve when is the integral equal to 0? Well, it must be when the area above is equal to the area below. Because if I was to work out the straight integral, they would then cancel and I'd get back to 0. So using this graph, we can actually answer this question, even though we don't have a displacement graph, because we're just going to simply work out when is the area above the axis the same as the area below the axis. Okay. Well, by symmetry, we would think that it's going to be at t equals 4. Because I'm assuming these two triangles would have the same area. The base times height's the same, so logical those triangles are the same. This rectangle has an area of 3, and so rectangle area of 3, I would end up over at 4. So when t equals 4, 2007 wasn't just straight lines, they had some curves, made it a little bit more interesting. So similar idea, this one's a velocity time graph, and they're going to ask us some questions about this one. Using Simpson's rule, we're going to estimate the distance travelled from, t equals 0 to t equals 4. See, it's going to be an estimate because we don't actually know the equation of these curves, but we have been given some coordinates of some points. So we can use Simpson's rule to estimate. So the distance will be the area under our displacement curve. And so I'm going to use Simpson's rule with h on 3, y naught, 4y odd, 2y even, and so on. So our table of values, well, really, we've only got 3 points that we know. There's 0, 0, 2, 1, and 4, 5. So we'll use those points. And so it'll be 1, 1, and then it'll be 4 times the middle one. 6, that turns out to be. So we've travelled 6 metres, approximately. So the object, we're told, is initially at the origin, during which times is the displacement decreasing. Decreasing. So, displacement is decreasing when velocity is less than 0. Well, that means it must be when t is greater than 5 seconds if we have a look at our graph. Because we're saying when is that velocity graph less than 0? When is it below the t-axis? And that's when t is greater than 5. Estimate the time at which the object returns to the origin. So it's again saying, well, when is displacement equal to 0? We're back where we started from. So it's like the last one, where we're going to say, well, hang on, displacement is the integral of velocity. So we want to know when that integral is equal to 0. So when's the area above equal to the area below? So we're going to need our graph there. Now, from symmetry, again, I'm going to say those two triangles. So t, when it goes from 4 to 5, that will be the same as the triangle from 5 to 6. So I know those two bits cancel out. Okay. In part 1, we estimated the area from 0 to 4 to be 6. So what we now want to work out is when is this rectangle going to be equal to 6? Okay, so there's a rectangle there, and at some point, the area of that rectangle will equal 6. So area 4, I've called it. I know the height of that rectangle is 5. So 5a will equal 6, which is about 1.2. So another 1.2 seconds gets us to 7.2 seconds. The area above will roughly be the same as the area below. Sketch the displacement graph now. Now, I like to draw these underneath each other so I can sort of translate down important points. So there's the velocity time graph. So underneath, I'm going to draw a displacement time graph. Now, here's the key things. Watch carefully, because I don't think all of these things are on the notes. Right? So, for instance, I don't think these arrows are they? So watch. So the object is initially at the origin, so I've plotted the point 0, 0 in. Okay. Now, we estimated that when t is equal to 4, displacement was 6. So I can plot that point in, 4, 6. By symmetry, remember we have the triangle above, then the triangle below. So I know that when t equals 6, I'm also back at 6. We said the area of this triangle is 2.5. Oh, well, we didn't say it, but we can work it out, sorry, because base times height, half of that will be 2.5. So therefore, halfway between 4 and 6, I must have travelled another 2.5. So I know when t equals 5, I'm at 8.5. We just worked out that it returns to 0 at 7.2. So I'll plot that point in. So I've got a few points there. Okay. This is a little bit of guesswork, I suppose, but if we look at the original graph, there's no question that v is steeper between 2 and 4 than it is between 0 and 2. Now this is a velocity graph, and we're saying it's steeper. So what does that mean? It means the particle must have covered more distance because the area, another way of looking at it is the area is greater as well. So it covered more distance. So therefore, and I'm just guessing, but where I plot 2 is going to be below halfway from 0 to 6 because more is going to be covered in the second bit than the first bit. So that's just a bit of a guess where to put that point. Now, when t is greater than 6, velocity is a constant. I have a horizontal line. Now we're integrating to go from velocity to displacement. Integrate a horizontal line, I know I get an oblique line. So I'll join those 2 points up. So I've got a piece of the graph so far. That's going to be a straight line. Now there's the rest of my graph. Why? Between the points B and D, I have an oblique line. Integrate an oblique line, I'm going to get a parabola. And so I've drawn a parabolic type of shape there. Now between A and B, again, it's guesswork. I'm thinking it's kind of parabolic. So I get some sort of curve which might look like a piece of a cubic going in. So that bit, as I say, a bit of guesswork there for the last part of the graph. Oops. That was it for that. So that's my guess. But it's the sort of thing as long as you can justify what you're doing, then you're not going to worry if it's out a little bit and what have you. Okay, another one of those sort of ones. 2005 paper had this interesting one. This one is also a velocity time graph. And we're told initially it's at the origin. So they want to know at what time is the displacement a maximum. So displacement is a maximum. Okay, well, again, 2 ways of thinking about it. Displacement will be at a maximum when the area is the most positive it could be, which would be here at 2. Or we could think of it as, oh, well, if I was to find the maximum, I would have differentiated and said the first derivative, which is velocity, is equal to 0. When is velocity equal to 0? Again, that's when it equals 2. So either way, it's going to be at t equals 2. At what time does it return to the origin? So you can see there's similar sort of questions that they're asking. Returns to the origin. Okay, when is displacement equal to 0? Area above equals area below. Again, same idea again. When's the area above equal to area below? Okay, well, I know that rectangle there has a value of 2. I don't actually know the area of that particular shape, but I'm kind of assuming it's symmetric. So I really have to do that. So I'm going to assume that's symmetric and that area balances out with that one. So therefore I need to work out a rectangle. When is that rectangle equal to 2? At what point? Well, the width of that rectangle, I know the height of it is going to be 2. So 2w equals 2. The width must be 1. So my estimate is it ends up being at t equals 4. So after 4 seconds. Draw a sketch of acceleration this time. So this time, instead of drawing the integral, we're drawing the derivative, because acceleration is the derivative of velocity. So, okay, same idea. I'll draw the graph underneath, labelled a few key points here. Let's see how we can construct this one. Okay, I've got a couple of horizontal lines here. Differentiate a horizontal line, so differentiate a constant, I get 0. So I know I must just be on the x-axis, or t-axis in this case. So from 0 to 1 and from 3 to 5, I must be just sitting on the t-axis. What else do we know? From 1 to 3, again, bit of guesswork. I'm assuming that's a cubic. Sort of got that twisting, inflection type of... I mean, it's not y equals x cubed, but it's got that sort of inflection type thing. So I'm going to assume that's a cubic. It inflects at 2. I also know it's decreasing. So if I differentiate a cubic, I would get a parabola. It'll be stationary at 2. And I know it's going to be below the x-axis, because decreasing derivative would be negative. So I've just drawn in a little parabola underneath the axis there. All right, next bit. 5 to 6, again, I'm assuming some sort of symmetry. So I think it's the same sort of shape. It's probably the same cubic. So it's logical that when I differentiate this, I would get the same shape as the other parabola down here. But this time it's increasing, so it'll be above the axis. So I think we get something like that. So that's my guess for the sketch. I hope so. Alrighty, there we go, 3C.